let's get this little presentation started. This is something that I put together specifically because I felt passionate about RIST, and I also felt that some of the things that we need to share are things that not everybody realizes. So that's kind of how I came up with this theme of sneaky great. You know, maybe a little bit too topical. Maybe that'll look dated in a few years, but what the heck. So really, I often hear people asking the question, why RIST? Okay, and I don't think that that's the right question. I think the right question is, why is RIST open source and open spec? Okay, and to me, that's really the heart of the matter. That is one of the primary reasons why RIST is the best spec that's out there today for high performance video transport over unconditioned network. And the answer to why open source, why open spec isn't a simple, well, because we decided to do that, which of course we did, but because of the benefits that it drives to the users and the implementers in the marketplace. So I'm going to go through a few slides. We're going to talk about, why I feel RIST has some cutting edge superior technology, why it has a wider range of capabilities, and why we have greater freedom for implementers. So the main motivation for RIST, widespread demand for reliable transport over unconditioned networks. So there's all kinds of networks that we don't have control over. We don't have private networks going everywhere we want. We want to be able to use the public internet. We want to be able to use all kinds of wireless connections, Wi-Fi, 5G, if it ever makes it outside of the core cities. Anything else that we can hook up. Maybe one of these days we'll be able to use the new Starlink stuff, but from what I've read so far, not quite yet. That's a technology that has a lot of work to do to get it to be the point. Even RIST can't fix no connectivity. And the other place where RIST has a lot of applicability is in long haul global links. As you go farther on the internet, as you go over longer connections, the native error rate of your network goes up. So you need some sort of a reliable way to work with a network that's going to lose packets from time to time. The other motivation for RIST was the lack of available open standards. All of the things that were out there at the time when we started RIST, which was back in 2017, were various sorts of proprietary. Some of them were open source. Most of them were just totally proprietary walled gardens. In other words, if you wanted to interface with a company that had a RIST-like product, something offering very high reliability using ARQ, you had to actually install their software. You couldn't just figure out how to connect to it. That's changing a little bit, but still RIST is definitely the leader in terms of openness. We have completely open specs. We also have completely open source code that anybody can download and use to their own delight, and that's coming along shortly. And a lot of the existing solutions were technologically inadequate. So they were built on outdated specifications. They had limited performance. So RIST was developed by a multi-company development team. A lot of the folks that you're going to be hearing talk today were involved in the development. And what that means is, rather than being a monoculture where one group of people decide what's good for the market, what's not, this is very much a team of rivals. We are, all the people that are active in the RIST community today have their own viewpoint. We're constantly challenging each other to produce the best possible spec that we can, hopefully avoiding things like creeping elegance, which is one of my pet peeves. And the idea here is that you get a lot of different perspectives. If you look at the names on here, we have users, we have implementers, we have pure technology plays. All of those companies have a viewpoint, and the people in those companies have a viewpoint. And together, their actions make RIST what I feel is one of the most robust specifications that's on the market today. Very short timeline. RIST activity group was formed 4 years ago last month. Okay, we started doing interops in 2018. We released our first spec in October of 2018, so that's only 2.5 years ago. We published a new version of the main profile in March of 2020. That's a significant advance forward in terms of encryption and other capabilities. And then we have our RIST profile scheduled for the summer of 2021. So there's a lot of development work that's been done in a very short amount of time. Now, one of the things I really like about RIST is that it's built on a secure foundation. And to understand what I'm saying, I put some bricks on the slide. So if you look at RTMP, which is still one of the very most popular formats that's being used today for live video contribution, if you go look at the actual RTMP spec, it was published in 2012, hasn't changed, which is probably a good thing for it, although it doesn't include, some of the niceties like encryption and, all the other modern tools, tunneling, all those other good things that you might want to expect in a more modern protocol. And it's built on, a couple of very rock solid standards that are out there, TCP and IP. But those are the only normative references in the Adobe RTMP spec. If you look at SRT, the only normative reference in there is a UDP spec. It's built on top of technology called UDT that never made it out of internet draft status back in 2010. And there is a SRT draft going through the IETF. That's been ongoing for about 1.5 years now. But it's still a draft. It's still not a standard. It's not a spec. It's not something that's finalized and ready for people to build on. When you contrast that with RIST, you see a vastly different picture. There's a lot of proverbial bricks in this wall. You see a lot of the underlying technology, including some of the key SIPT specifications, were built into the simple profile of RIST. You see that there are enhancements, particularly in the area of encryption, that were built into RIST main profile. And this really goes to the heart of what's, to me, sneaky great about RIST. We rigorously try to avoid developing anything new. The goal of the RIST activity group is to reuse and build upon as much technology as we possibly can, whatever's out there, that is going to suit the needs. We don't want to become encryption experts. We don't want to create whole new packet formats. We want to use that existing technology and build something that's on a secure foundation and is really ready for people to move things forward. All RIST specifications are published and they're comprehensive. In other words, everything you need to build a complete RIST solution is in the specs. They're available free of charge on the VSF website. You don't need to download anything other than the specs, and you know everything that you need to know to implement RIST. So any developer can read those specs and implement a solution. But if that's not your bag, if you don't want to write some code, we have downloadable open source code from the LibRIST. It's a simplified license. Anyone can use the code. They can modify the code. They can put the code into their own proprietary products, sell products that run on that code, and there's no mandate to put things back. This is about as liberal a license as you can get. For developers, this is nirvana. They can do what they want with the code. They don't have to use it. They can change it. If they make something, if they make a great improvement, they're not required to put it back into the source code. It's very much developer friendly and innovation friendly. The result of this is that, developers can follow many paths to create a RIST product. One of them is LibRIST, of course. There's been over 745 commits to date. That's a fairly good amount of activity of a group that's very engaged in making sure that LibRIST is as good as it can be. RIST technology is also available on AWS in their Media Connect product. I know this is a little bit commercial, but it's just pointing to the fact that RIST is not just a bunch of little companies. We're engaged with major network providers, and they're adopting the technology today. So what are the technology benefits? So first of all, the design philosophy, as I mentioned, is use what already exists. So any COP3 SMPTE ST 2022 receiver that was in the market when RIST first came out could receive a RIST stream. The simple profile stream is compliant with the 2022-2 specification. So if they were connected, if the network was error-free, they would work perfectly. They would get all their packets. They'd be able to decode a video image, and life would be good. RIST is also codec agnostic. We don't tell you how to compress your video. Yeah, we recommend in certain profiles that you use H.264 just because it's very widely used, but it's not required. RIST is not written around a specific form of compression. So again, developers have their freedom. The error correction parameters are set up by the implementer. So you can decide as an implementer, how long do I want my buffer to be? How soon do I want to resend bad packets? How do I ask for bad packets? And the beauty of RIST is that even units that might have different settings will still work compatibly. It might not be optimal if this unit is using a 5-second buffer and this unit thinks you only have 500 milliseconds. You might try to retransmit some packets that might not be received properly. But when you put it all together on a basic level, those units will still talk. They'll still get some communication through. There's no central force guiding us and saying you must and you shall do certain things certain ways. And the other thing is that we've definitely tried to stay away from encryption. Encryption is an art. I have tremendous respect for the people that are heavily involved with that, but it's hard to get right. One mistake can make your entire protocol unusable and have to be revised and changed and things like that. There's always exploits coming out, things like that. So we don't try to do that. We use the encryption that's available through the IETF and other well-known standards. So a lot of people say, well, I don't want to use RIST. FEC does everything that I needed to, and that's fine. There's nothing wrong with FEC. RIST actually supports FEC. It was built into the specifications from the very beginning. But the problem with FEC is that there's a sweet spot. If you have too many errors, what happens is that FEC will break down. If you have too many errors, if you have more than 2 errors in a block for the row column FEC, and they happen to line up, that you won't be able to recover your whole block of data. That could be a frame's worth of video, whatever. So there's always an upper limit to how much correction FEC can do. On low loss networks, FEC is wasteful. If you apply a lot of FEC to your streams and you don't need it, all the extra FEC packets are wasted bandwidth. You could have redeployed those to do something else. With RIST, the correction scales to the amount of errors. If you have a very low error network, you have very low overhead for correction. If you have a lot of errors on your network, yes, you need more bandwidth to correct those errors, but again, that's the trade-off. Higher error rate means you need more correction power, and RIST can scale up to that. It can handle situations where you're losing over half of your packets. RIST has been shown to work. RIST also is very flexible from a network standpoint. It supports network bonding. So if you need RIST to go over multiple channels, you have multiple Wi-Fi connections, etc., what you have is a very simple system whereby each packet has a serial number associated with it. RIST receiver can receive all those packets, put them back into order. RIST receivers also support seamless switching. So if it gets 2 copies of the same packet, it'll pick one of them and ignore the other one. The beauty of that is that gives you a tremendous amount of flexibility for tunneling packets, for combining things through. You can have bidirectional tunnels going on. You can have a tunnel gateway in the middle of your network that takes individual streams and combines them together. You can even put different streams on different tunnels, so you can have different network technologies supporting different ways to get your packets from one place to another. So you can combine fiber with wireless, with satellite, and have all those work together in harmony and supporting the main goal of getting as many different ways to get packets from the sender to the receiver as possible. Incredible flexibility. No other technology offers this kind of capability that's available, outside of a walled garden today. There's been different versions of RIST. Simple profile is out. The RIST main profile, which is released, has a baseline level, has a DTLS level, has a PSK level. DTLS is used for point-to-point connections. PSK is used for point-to-multipoint. RIST supports multiple types of encryption. We support AES 256, which is considered secure. We also support AES 128, which isn't secure, but is required by regulators in some markets. We have a mechanism to share keys with multiple endpoints. We support key rotation so that if you have a key running for too long, it becomes easier to crack, so we can change it. Again, that's at the discretion of the implementer. We do authentication, so we make sure the endpoints are who they are before we connect to them. We make sure that the packets don't get corrupted so that we get a packet from point A to point B. We make sure that nothing's changed inside of that by a malicious actor. And we also have a way to do secure key distribution so we can manage multiple endpoints that are out there. The RIST Advanced profile is projected to include a VPN service, which is also extremely exciting. RIST also plays nice with others. So there's no built-in bandwidth or buffer limits. We can work with high-speed RTP streams like uncompressed SMPTE SD2110. But there's lots of installations on the market today that work with high compression codecs, AV1 or HEVC or whatever the new flavor of the month happens to be. That'll all work over RIST. We can handle non-RIST traffic in our tunnel, so we can bring in TCP, we can bring in control signals, we can bring in anything that you want to put through a RIST tunnel will go through there. And we even have a reduced overhead mode to get rid of some of the packet headers that you don't need once you're inside the tunnel. We have a RIST test server that's available for anybody to connect to and try out. And I think somebody will be talking about that a little bit later on. And we also are in liaison with the WAN IP activity group within the VSF and the ground to cloud, cloud to ground activity group inside the VSF to form a common basis. So RIST is a relatively new arrival. It's only 2.5 years old. RIST Forum now has 140 members. It has superior technology, as good as or better than anything else on the market today, handling packet loss rates of 50% or higher. And that's been demonstrated in live field events. It has a wider range of capabilities and options. It's available in VLC, Wireshark, GStreamer, UPipe, all these great open source tools and efforts. And it has a great amount of freedom for implementers. So much more flexibility than you have with a single uniform code base. There's no developer restrictions. There's multiple different implementations of RIST out there today. And I would say that it's a very vibrant and growing ecosystem. So thanks for your time. And I'll turn it over to our moderator, and we'll move on to our next speaker unless there are any questions.